So here we are at the last page. I know you're excited to be at the last page. We'll use this. Fill in the study guide. You'll be able to use the study guide on the test. I'm going to take ideas from this study guide. Most everything I marked off. A couple of things. I will use actual questions from the study guide on the test, or at least give you the formulas for that. Linear expansion and volume expansion will be two of the problems that are actually on the test. So here goes. Number 11, in an area that experiences both hot summers and cold winters, why would the time of year that overhead power lines are installed change the way wires are strung? Well, obviously because of expansion during the summer and contraction during the winter, we need to know what's going to be happening later on. If you expand them and if you install them in the winter, you want them to be relatively tight, because if there's expansion in the summer, you don't want the wire to sag too low, then it gets in the way of other things. If you install them in the summer, it's going to contract. So if you install them real tight in the summer, then when it contracts in the winter, it's going to break the line and you're going to not have any power. In making a thermometer, why is it important to have as little thermal expansion as possible in the glass? There are a couple of reasons. You know, if the thermometer expands up and down like the mercury inside, you know, the lines between the degree markings are going to expand as well, and so you're not going to have an accurate reading. Or if the glass is too thick and the glass expands too much, it's also going to expand inward as well. It's going to push the mercury up. It's going to create less area inside for the mercury to exist, so that the levels are going to change due to expansion, and that's not how we want it. We want the thermometer to stay relatively even, and we only want the liquid inside to expand. Now they use alcohol inside, they don't use mercury. And so we want the alcohol to be able to expand upward the right amount. And so let's move to 13. 13 is written up here. Pardon me. You have an aluminum baseball bat, and on a specific day, the temperature is 20 degrees Celsius. That's a normal, everyday occurrence, I guess. Spring day, 86.4 centimeters long. And what happens if the temperature goes up to a much hotter day, which is 32 degrees Celsius? Well, you'll get some expansion in the aluminum. Remember, with our examples that we used previously, it took a lot of heat to make a noticeable expansion, and you're going to see that when we get to the end here, you can't notice this expansion. We're talking about what is that, 10,000ths of a centimeter. The 10,000ths of a centimeter is 3,000ths of a millimeter, and you can't even break millimeters down into 1,000 pieces that you could see with the naked eye. So you're going to see that there's no baseball bats grow that long when the day is much, much hotter. And that's why it's not that big a deal to use the same baseball bat over and over again, from the beginning of the season to the end of the season in baseball. And that's colleges get to use aluminum bats. Not a big deal. Eventually the pros will be able to use them if they can control it, but who knows. The math is here. To find the length after it's grown, you take the original length and then multiply by the amount of growth, and that's the coefficient of linear expansion times the original length times the change in temperature. And so I did all the math here. I'm going to let you see this. You can stop the video and go ahead and write that stuff in, and that's how we came up with this tiny bit of expansion. Pardon me. Explain why a bridge in Vermont must have larger gaps in in the expansion joints than the same structure built in Florida. And, well, we see that in Vermont, it gets really, really, really cold, but it also gets hot in the summer. So, because of the drastic amount of temperature extreme, uh, you need larger gaps. Because when it's really, 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 really cold, then those gaps, much farther apart. But then in the summer, it really does. The change of temperature is really, really extreme. So they're going to need that much more room to come together. Whereas in Florida, there's not a huge change in temperature. They don't get below zero. Um, I dare say they probably don't have very many days below 32 degrees. So, uh, as far as I know, anyway, I would imagine it's very much like Arizona in the desert. They get to the 30s, but never really much lower than that, and they get temperatures above 100 degrees. So you get about 90 degrees, but you can in Vermont in the 90s in the summer, but you get much, much, much colder weather, so the extremes are much greater. So let's move on to the last question. The last question says the volume of a copper sphere is 2.44 centimeters cubed at 12 degrees, and what's the volume of that same thing when it's heated up to 984 degrees? And we're going to see that because there's so much heat added to this, we're going to get some expansion, but even that expansion is not that enormous. Okay, you're going to notice even when we use significant figures, we've only gone up 2/10 of a centimeter, or 1/10.5 of a centimeter, and the actual expansion is just 11/10 of a centimeter, which is a millimeter and 1/10. So it's not that much in terms of volume. So the volume is just like linear expansion. It's the original volume times the coefficient times the original volume times the change in temperature. So we're going to start with our 2.44 cubic centimeters, not that big a volume. The coefficient is 48 times 10 to the negative 6. Again, not a huge number, but bigger than most of the rest of them. So metals expand a lot more than do other substances that we've been talking about. And it looks like copper, since it's a good conductor, expands more. And so we use all those numbers, we do the math, and it only comes out to 0.11 cubic centimeters of change. And we add that to our original. Now we have 2.55, or in sig figs, because we've gone with 48, which is 2 sig figs. And we have 2.6 cubic centimeters of volume expansion. And like we said, not a huge amount. These things aren't growing enormous amounts. And remember, we put 972 degrees of temperature change in here, and it only expanded a little over a millimeter. Take that into account when you're talking about these expansions, or when you're looking at these expansions. I know it's difficult to look at. These formulas look ridiculous to you, but there's not that much change. It does exist, but not that much.